We are studying VLSI design, and we will continue studying pseudo and MOS logic. We started studying pseudo and MOS logic in our last lecture, lecture 9.1, and today we'll continue it. Right. How would I continue? By giving a recap first. Right, so I'll give a recap, a small recap of the last lecture. And the recap is that uh, uh, pseudo and MOS circuit can be represented as an nMOS logic array, where the nMOS logic array is the same as it is in the case of CMOS. But the nMOS array is a bit different. The PMOS array is a bit different. It consists of only one transistor. And this one transistor is always on. It's never off. Why is it on always? Because the gate is connected to ground. When it is ground, this voltage VSG between the source and the gate of this PMOS is greater than its threshold voltage VTP, and it is on. It is always on. So for input combination for which the input is not the input is such that the output is a logic high, we don't need any switching, because the output high is it's readily available at the output. Right, so we solved a NOT in last lecture. We studied pseudo and MOS NOT, and we computed its VOL in our last lecture, V output low. And we studied that VOL isn't exactly zero, because for input combinations for which the output is low, this one transistor and this whole array, both these arrays are on. Therefore, we cannot have a VOL exactly equal to 0 volt like we have in case of CMOS. So it's slightly greater than what we had in case of CMOS. Right. This is a small recap from lecture 9.1, the last lecture. Right. In this lecture, we will only solve a simple example where we are given a bias CMOS. This is sorry, by CMOS, it's not by CMOS, it's a pseudo nMOS. So pseudo nMOS gate with VDD5, VTN 0.7, VTP 0.85, kappa n 120, kappa p 55, and aspect ratio of n. All these things are given, and it is also given that it is a pseudo nMOS NOT. So in part A, we have two parts of this problem. In part A, we are given VOL 0.3 volts. As I've already told, it's not 0 volts. It's slightly larger than 0 volts. And we are given aspect ratio of P. And we need to find, we are given VOL, and we have to find aspect ratio of P. It's unknown. We have to find aspect ratio of P if VOL is given. In our last lecture, we studied that IDN is IDP when we have input logic 1 and when the output is logic low. And this nMOS transistor is in its linear region. PMOS transistor is in its saturation region. This is the equation for current ID when nMOS is in linear region, and this equation is for ID when this PMOS is in its saturation region. So we can go ahead, divide these, they both are This 2 and this 2, they cancel out, and then we can divide beta n over beta p, this whole stuff. If we divide it here, this means this whole stuff will go in the denominator here. So beta n over beta p. Let's put the values. VDD is 5, it's given. VTP is given to be VTP is given to be 0.85, this one. Input all these values, beta n over beta p comes out to be 6.92. And we know from chapter number 7 that beta n is kappa n aspect ratio of n, beta p is kappa p aspect ratio of p. Kappa n and kappa p, these two values are given. Kappa n is 120, kappa p is 55. It's given in the question. So put these values here. Aspect ratio of n is also given. This is 0. This is 4. So we have 4, this 120, 55. Aspect ratio of p is unknown, and this 6.92 is the ratio. So in this equation, we have only one equation, one variable, solve for it, and aspect ratio of p comes out to be 1.26. And this is very interesting that aspect ratio of p is smaller than the aspect ratio of n4. And we have studied for regular CMOS circuits that in order to achieve a symmetric node, we need to have aspect ratio of p greater than aspect ratio of n. So this is another observation in case of pseudo nMOS, that aspect ratio of p is usually larger than aspect ratio of n. Aspect ratio of p is, smaller than the aspect ratio of n if we want to keep VOL low. So this may be a disadvantage, that we have to have larger nMOS transistor compared to PMOS in order to have smaller VOL, which should ideally be 0. Right. In part B, we are given aspect ratio of P and all other things that are given here up till here. Right. All these things. Plus we are given that aspect ratio of P is 3, and we need to find VOL. So we'll use the formula that we studied in lecture 9.1, the same formula, and we'll keep on putting things in. VDD minus VTN, 5 minus 0.7, 5 minus 0.7 squared. So beta P can be written as kappa P aspect ratio of P. So this kappa P is written as aspect ratio of, this beta P is written as kappa P aspect ratio of P. And this beta n similarly can be written as kappa n times aspect ratio of n, which we have done here. We know kappa P, we know aspect ratio of P. It's given 3. We know kappa n, we know aspect ratio of n. So we put everything that we know, and VOL comes out to be 1.54 volts. So we'll keep on studying high-speed circuits in our upcoming lectures. Thank you.